Okay, so we're going to talk about something called the max flow min cut theorem. So I'll just go ahead and state the theorem first, and then we'll talk about it. So it says that the maximum flow, or maximum value, max value of an ST flow is equal to the minimum capacity over all ST cuts. And what's really interesting about this algorithm, actually there's two things. So note one, the max value, oh geez, here we go again. I've been having trouble with this thing. Okay. I'm not sure why it's moving around on me. So let's see. Let's get back to this. Note one is the max value is a primal linear program. And what happens is you can talk about the min cut is the dual LP. And so do you see how that works now? If this is the dual, then the minimum capacity is equal to the maximum value of the primal at the optimum value, right? So min cost is equal to max value. So this is just an example of the dual theorem. If you take a look, well, we won't spend too much time on this because we're not going to actually formulate the dual, but we did talk about how to formulate the primal. Okay, what I wanted to talk about instead was a little bit more practical, and that is, given the flow, can you find the min cut? So here's an example here. We were given a flow, and we were trying to see, well, where's the min cut going to be? So for example, suppose that I just make an arbitrary cut right down the middle. Here's my cut. What's the capacity of that cut? Well, the capacity of the cut is the sum of the capacities from A to B, right? So for this cut, it would be 8 plus 4 plus 9. Okay. Okay, that's 21. Okay, what we know, of course, that our flow is 19. So I need to find another cut. So let me take this cut out. Oops. Oh, I'm erasing all kinds of things here. Okay. We had this one and this guy and this guy. Okay. So is there another cut that I could use? Well, notice that if I just we'll just take another random one first. How about if I take this cut? Well, notice then that the capacity then is going to be 10 plus 10, which would be 20, and that's bigger than the 19. So there must be another cut somewhere. I wonder where it is. I think I see it. So the idea that is mentioned in the notes is that you want to go from the source to the go out. You want to include in set A all of the nodes that you can reach from source S. So in this case, I can reach 2, and so my cut is actually going to come this way. Okay, let's see, what did we have there in 9? I think we had 9, right? Let me get back to my point here, 9. Good. And so what is the capacity of this cut? Well, it's going to be 10 plus 9. So the capacity of this cut is 19. So there you go. If A is equal to S2, right, then the cut from A to B is equal to 19. And so the flow is 19. And so that is the cut that gives you the the max flow. Good. All right, so that was fun. I'm going to pause for a moment, and what I'll do is I'll construct another example, maybe different from the one in the notes, so that you have another one. Maybe I'll do the first one in the book. We'll do that one together, and then you can take a look at the homework. Okay, we'll pause there for a second. All right, so what you're looking at here is problem number 1 in the book. Number 1. And again, we want to find the max flow. So the way to start is just to start randomly picking a few paths. And so, normally I'm just going to pick off the path along the top and along the bottom just to start. So let's just go ahead and take S1, 3T. And let's go ahead and take S2, 4T. Okay, so the capacity here, or the bottleneck, is going to be 2 there, right? And the bottleneck underneath looks like 2. Okay, so then go ahead and put down our flows here. So this is going to be 2, 2, and 2. And then we have 2, 2, and 2. So far our flow value is 4, right? Good. All right. Now I'm going to go ahead and take a moment. I'm going to pause this, and I'm going to go ahead and write down the residual. Oh, maybe you can watch with me while I do it. It should be fun. Let's see. Well, I'm going to be able to read this. S1, 2. Let's see how fast I can do it. 4. Oops. T. Okay, so I've got backwards 2, forward 6 now. Let's see, this one was backwards 2, forward 1. This one would be just backwards 2. Okay, this one was just forwards 1, forwards 3. This is backwards 2, so forward 5. And this one was just backwards 2. Good, so there's my residual. Is there anywhere I can go from here? I wonder, do we see that? I think we can go from S to 1, and then from 1 to 3, or I guess we could go from 1 to 2. Oh, we can go to 1 to 2 next. 3 to 2, and then 2 to 4. Oops, I forgot 1. This was back 2 and up 5. Okay, and then we can go, that's our last edge there. Okay, so that's our path now. S1, 3, 2, 4, T. And our B value, let's see, 6, 1. Oh, I guess 1's going to do it, right? So putting in a flow of 1 is going to mean, I'm just going to go ahead and change that to a 3 and a 5, right? And then this is going to be 3 altogether up on top. And there's not going to be anything left down here. Let's see. This is just going to be a 1. So there's a 1 backwards. And a 2 forwards. Okay, and then we have 3 back and 4 front. And then, let's see, 3 back and 4 front. Is that right? I believe so. Good. All right. So, what's left? Could I still move around in here? I think we can. By the way, this is the nice thing about a residual graph is you can really see what's going on. So now we can go this route from 1 to 2, right? And then we can go from 2 to 4 and 4 to T. So that's going to be our second path here. S1, 2, 4, T. And the B value here is 1, right? So that's going to take that to 4, and then I'll just have 4 left there. This is going to have a backward 0 with a 1. Let's see, this one's going to go backwards 4 and forwards 3. And similarly, this one will go forward 4, or backwards 4 and forwards 3. Good. Is there anything left now? Is there anywhere else I can go? I believe we are stuck here, right? Because if I move from S to 1, is there anything I can do from there? No, I'm stuck. So what's my flow now? 2, 2, 1, 1, is that it? 4, 5, 6, whoops. So my flow is 6. Looks like it. So flow is 6. Now, can we find a minimum cut? Let's see. How about, so this is, it's probably easier to do it up here. Although I don't have my updated numbers. That would be a 4, 4. 2, 2, that was a 3, 3. This was a 1, 1. That's probably enough. Because I think, do you see one with the capacity of 6? Did you see it? So on the residual graph, like we were saying before, on the residual graph, look for the nodes that are reachable from S. And it looks like just one is reachable from S, right? And so is that the cut? Is this the cut? Well, let's sum the capacities. 3 plus 1 plus 2. What's that? That is 6. That is the cut. Congratulations. We have now found the max flow min cut. Good. It's your turn now. See you later.